Going to be going over section 2.5 of our virtual pre-calculus text on polynomials. We're going to be looking at how to apply Descartes' rule of signs. A sample problem that we're going to be covering in this presentation is pictured here. Find the possible numbers of positive real zeros of this given quintic with 4 terms. Don't forget there are 5 practice problems at the end of this presentation that I would like you to try out in order to gain to demonstrate mastery of the contents of this presentation. To gain access to our entire pre-calc, Algebra 1, 2, Geo, and Calculus courses, just take a look at the links in the description below or visit our website at Mathgotserved.com. Alright, to get us started, we're going to take a look at what Descartes' rule of signs is. So this is our website, Mathgotserved.com. We're going to scroll down to our must-know formulas. And then we're just going to advance the slide all the way down to Descartes' rule of signs. So let's go ahead and do the advancement. Let's go all the way to Descartes' rule of signs. All right, there you have it. Descartes' rule of signs. So they basically help us to determine the possible number of positive and negative zeros of any polynomial function. All right, so number 1 is for positive. It tells us that the possible number of positive real zeros of a function f of x is equal to the number of sign changes of f of x or multiples of 2 less. So when we're talking about multiples of 2, we're counting down by 2. Okay, so think about it that way. If you have your result is an even number, then you just count down by even numbers. If your result is an odd number, then you count down by odd numbers. Number 2, the possible number of negative real zeros of a function is equal to the number of sign changes or variation of f of negative x. So you see the difference here. For the positive real zeros is f of x. We're looking at sign changes for f of x. But for negative real zeros, we're looking at f composed with negative x. Okay? So the number of sign changes of f of negative x or multiples of 2 less than that. So counting down by 2's also. All right, so the instructions for the examples we're working on are for us to state the possible number of positive and negative zeros of the given functions, and then we're going to summarize the possible complex zeros distribution using a chart. Okay, so for problem number 1, let's say we have the given polynomial f of x, minimize that, equals 2x to the 5th power plus 3x to the 3rd minus 3x to the 2nd plus 5x minus 1. Okay, so this is the quintic polynomial with 5 terms that was presented at the opening of this presentation. So let's go ahead and take a look at this. We're going to start off with the possible number of positive real zeros. Okay, so positive real zeros. All right, so one thing you want to keep in mind is that when you want to start working with the function, you want to make sure that the polynomial meets the following criteria. Number 1, it has to be written in standard form. So we write in standard form. And secondly, you do not need placeholders. All right, so no need for placeholders. So if you're missing a degree term, you do not need to insert a placeholder for that. So let's say you were working on synthetic division or long division, then you have to insert placeholders after placing it in standard form. But when we are working on Descartes' rule of signs, you do not need placeholders. All right, so let's write the polynomial f of x is equal to 2x to the 5th plus 3x to the 3rd minus 3x squared plus 5x minus 1. So for the possible number of positive real zeros, we're looking for the number of sign change or sign variations for f of x. All right, so let's outline what the signs are for each term. The first term is positive. Second term is positive. The quadratic term is negative. The linear term is positive. And then the constant is negative. Okay, so you notice that it's already in standard form, 5, 3, 2, 1, 0 in descending order of degrees. And even though the quartic term is missing, we didn't insert a placeholder for that because the sign of 0 is not applicable. 0 doesn't have any orientation, okay? All right, so let's see here. So we're going to count the number of sign changes or sign variations. So we have, what do we have? From here to here, that's from positive to negative, that's the first sign change. And then from negative to positive, that's another sign change. And then from positive to negative, there goes another sign change. So we have first sign change, second sign change, and then the third sign change. So we have a total of 3 sign changes. Okay, so let's write it down. Number of sign changes or variations is 3. So what does that tell us? Well, using Descartes' rule of signs, we can figure out the possible number of positive zeros. Okay, possible number of positive zeros are going to be either the total number of sign changes, which is 3, or multiples of 2 less. Okay, so if we count down from 3 by 2's all the way down to 0 or 1, we have 3 minus 2, which is equal to 1, and we can't go any lower because we're going to go negative. All right, so our answers are either 3 positive real zeros or 1. All right, so this is what it means by the number of sign changes or multiples of 2 less. You're counting down by even numbers or by 2's. Okay, all right, so that's that for positive real zeros. Now let's take a look at negative real zeros. So for negative real zeros, we're gonna start with what we had originally. The original function is 2x to the 5th plus 3x to the 3rd minus 3x squared plus 5x or 15x plus 5x minus 1. Okay. All right. So we're looking for f of negative x. What is that? F of negative x. So f of negative x just simply means that you replace all the x's in f of x with negative x, right? So let's bring that down. So it's going to be 2 times negative x to the 5th plus 3 times negative x to the 3rd minus 3 times negative x squared plus 5 times negative x minus 1. Okay? All right, so it's a simple way to help you simplify this is just remember that if the power of a term is even, you keep the sign, and if it's odd, you flip the sign. Okay? So let's write that down. Even power is even. You keep the sign, and then odd, you flip the sign. All right, so this one right here is 5, so it's odd. This is 3, that's odd. This is 2, that's even. This is 1, that's odd. And this is negative. This is 0, so that's considered even, 2. All right, because it's constant, it doesn't change. So what am I saying here? So all the terms with odd powers, you flip their signs. That's what's going to come out. And then all the terms with even powers, you keep the sign. The reason is that when you're pairing up odd signs, you're always going to be left with one negative, which makes the entire expression negative. And then if it's even, all the minuses pair up, so it becomes positive. Okay, so this one you flip the sign, negative 2x to the 5th is just a neat little shortcut. This one you flip the sign, negative 3x to the 3rd. This one you keep the sign for the quadratic term. Linear term has an odd power, so you flip the sign, 5x. And then this one, you keep the sign for the constant power 0. So that's what you have right there. All right, so remember, for the negative real zeros, we're looking at the sign variations or sign changes for f of negative x, which is what we just did. So let's outline the signs of each term: negative, 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 negative. So how many sign changes or variations do we have here? Absolutely none. All negatives, okay? So number of sign changes or variations is 0. So what are the possible number of negative real zeros for this case? Possible number of negative real zeros is 0. Okay, so there goes the answer. So now what we're going to do is we're going to go ahead and organize our possible number of zeros. Let's organize a chart to help you see what could possibly happen when we solve this problem. All right, so let's make a chart here. We're going to go more into this in the next lesson on the fundamental theorem of algebra. So this is just getting you ready for that. Okay. And bam. All right, so in the first column, we're going to be looking at the real zeros, okay? So for the real zeros, I'll write that again. So this first two are real zeros. So for the real zeros, for all real numbers, okay, they're either positive or negative. So for the real zeros, it's either going to be positive or negative. So let's look at what we have here. So we have positive or negative. All right, so in our solutions, we notice that the real zeros and negatives there are no negative zeros in this particular problem, so 0, 0. But for positive, you could either have 3 positive real zeros, or you could have 1 positive real zero. All right, okay, so your zeros could either be real, or guess what? They could be imaginary. Okay, so let's take a look at that. Concerning imaginary zeros, how many could we have? Well, we just have to use imaginary. We just have to use FTA to figure this out, okay? So FTA tells us the total complex zeros that we have. So the total complex zeros, according to the FTA, is basically the degree of the polynomial. The degree of the polynomial is 5, so we know for sure you're going to have a maximum of 5 complex zeros, combination of positive, negatives, and imaginary where applicable. All right, so let's work this out. So if you have 3 real zeros and if you have 3 positive real zeros and 0 negative real zeros, and there are a total of 5, that means you must have 2 imaginary zeros. So 3 plus 2 is equal to 5. Perfect. And then if you have 1 real zero and 1 positive real zero and no negative real zero, and a total of 5 complex. Remember, the complex is a combination of real plus imaginary, okay? So the mathematics has to work out. So if you have 1 plus what gives you 5. If there's only 1 real, which is positive, and there are a total of 5, a combination of real and imaginary, then there must be 4, oh snap, wrong color. There must be 4 imaginary zeros. All right, so this is just the total summary of what the zeros look like. For more detail on how this works, we'd like you to watch our next presentation on the fundamental theorem of algebra, and then we're going to go in depth into finding not just the signs and numbers, but what they are exactly. All right, so here are the 5 practice problems that we promised to have you work on at the start of this video. So go ahead and pause this video presentation at this time. Try out these 5 practice problems. All you're doing is specifying the possible number of positive real zeros and a possible number of negative real zeros. When you're done, click on the playback button, and we're going to reveal what the correct answers are. Alrighty, welcome back. Hopefully you had a chance to try out the problems. Let's take a look at what the solutions are. For number one, the possible number of positive real zeros is just 1. Bam. One sign variation for f of x. And then the possible number of negative real zeros. We're looking at sign variations for f of negative x is 4, counting them by 2, 2, or 0. Bam. For number 2, the possible number of positive real zeros is just 1, only one sign variation for f of x. Possible number of negative real zeros, we're looking at sign variations for f of negative x. In this case, we have it's either 4, counting them by 2, 2, or 0. For number 3, the possible number of positive real zeros is the number of sign variations for the original function f of x, only one sign variation. And then the possible number of negative real zeros, we're looking at the sign variations for f of negative x. Remember, for odd powers, you flip the sign. For even powers, you keep the sign. If you do that, you're going to have 4 sign variations or multiples of 2 less, 4, 2, or 0. For number 4, possible number of positive real zeros, sign variations for f of x is either, we have 2 sign variations or multiples of 2 less, 2 or 0. Okay, and then for a possible number of negative real zeros, we're looking at the sign variations for f of negative x. Okay, so that's going to be 2 or 0. Last but not the least, number 6, or number 5, sorry, the possible number of positive real zeros for number 5 is sign variations for this function. There are 2 of them, so it's going to be 2 or multiples of 2 less, 2 or 0. And then the possible number of negative real zeros, we're looking for the sign variations for f of negative x. There are 2 sign variations for f of negative x, so we have 2 or multiples of 2 less, 2 or 0. Alrighty, so here are the solutions to the 5 practice problems. How well did you do? Did you get all 5 correct? Let us know how well you did in the comments section below. Thanks so much for taking the time to watch this presentation. Really appreciate it. If you found the contents of this tutorial helpful in your studies of polynomial functions and Descartes' rule of sign, do give us a like or a thumbs up. Do not forget to subscribe to our channel for updates to other presentations such as this. Tons of support resources can be found at mathgotserved.com. Thanks again for watching and have a wonderful day. Goodbye.